In this episode, we're going to go over our second important fluid property, viscosity, which is unique to fluid mechanics, so we're going to spend a little bit of time developing an intuitive understanding of what viscosity really is. Conceptually, we can think of viscosity as a measure of the stickiness of a fluid to itself or to other materials, analogous to a friction coefficient for a solid. For example, water is a low viscosity fluid, whereas honey or oil are high viscosity fluids. So for water and honey from the previous example, there's a linear relationship between the stress and the strain rate. And that can be expressed mathematically as tau, the stress, is proportional to the strain rate, or the spatial gradient in the velocity dv dy. And this relationship is important because most of the things we do in engineering, most of our practical engineering applications are Newtonian fluids. Water, air at low speeds, oil, mercury, glycerin, most of the things we deal with on a day-to-day basis are Newtonian fluids. And so this relationship holds. And it turns out that the viscosity, or in particular the dynamic viscosity, which we'll talk about first, is the constant of proportionality between the stress and the strain rate. So we define that using the Greek letter mu, and we can now write tau, the shear stress, is equal to mu times the strain rate dV over dy. Okay? And mu, the dynamic viscosity, has units of Newton seconds per meter squared in SI, or pound seconds per foot squared in English units. So to get that intuitive sense that I mentioned in the intro, let's consider a simple geometry of two flat plates that are very close together with a small amount of fluid in between them. As you can see in the drawing above, we're going to apply a shear stress on the top plate and hold the bottom plate fixed so it won't move. The fluid that's touching the two plates is going to move either with some speed with the plate, and then the bottom stay at rest. And in this situation, a highly viscous fluid such as honey or oil, the flow will move slowly. As we apply the shear stress, mu is high, so the du dy will be low. The flow will move slowly, and so the upper plate will ultimately move relatively slowly. In contrast, if that fluid in that interface, between the plates, is water or alcohol, a low viscous fluid, then the upper plate will move much more quickly, because for a constant shear tau, mu is now lower. To keep tau constant, the du dy goes up, and then over that small distance of y, we now have a higher velocity once we integrate it. And this situation is actually pretty pertinent to a lot of engineering applications. This is what happens for skimboards. When you see someone at the beach running with their skimboard, they jump on it, there's a thin layer of water in between it. In a lot of mechanical engineering applications, there are two pieces of metal and a piston with oil in between them. And so this is a very common situation in many engineering applications, and viscosity is extremely important. Okay. However, a lot of our fluid analyses, we're dealing with force balances, and forces are often expressed, such as shear stress, as per unit mass rather than per unit volume, because force is mass times acceleration. So it's much more convenient to describe it as a per unit mass than a per unit volume situation, where the dynamic viscosity is really a per unit volume type unit. So from before we said tau is equal to mu times dV over dy. Okay? Well, to convert the per unit volume to a per unit mass unit, what we can do is divide by the density. So if we divide both sides by rho, we end up with a new quantity here, mu over rho, which we're going to end up using quite a bit. And we call this combination the kinematic viscosity. And we give that the Greek symbol nu. So now we have nu, the kinematic viscosity, which is nu, is equal to mu over rho, the dynamic viscosity divided by the density. And the kinematic viscosity has units of meters squared per second in SI, or feet squared per second in English units. And you immediately see some analogies here. Units of kinematic viscosity are the same as a diffusion coefficient for, say, salt or oxygen or heat. They have units of length squared over time. So we can conceptualize this as a coefficient of diffusion for momentum. It's the rate at which momentum in the fluid is transferred to other parts of the fluid. Okay, so that's the general understanding of viscosity. And so we gave you in this video a definition of viscosity as a kind of the stickiness of a fluid, and we covered two definitions of viscosity. One is the dynamic viscosity, which really defines is the constant of proportionality between the stress and the strain rate in a fluid. And then we gave you another definition that is on a per mass basis, which is more convenient for a lot of our force balances, the kinematic viscosity, which can be directly thought of as a diffusion coefficient for momentum in a fluid. In the next episode, we'll cover the next fluid property, surface tension.